our formulation of the principle of the least action will be 1 plus 1 dimensional, 1 spatial and 1 time dimension, but with a single particle. In a potential. But the generalization to, say, an arbitrary number of particles, in higher dimensions is obvious, okay? It should be immediate. There's some subtleties, but conceptually it's essentially the same thing. Okay, so before we formulate the principle of least action, we need to introduce some definitions and concepts. Okay, so any questions so far?
No, sir.
Okay. So we are in 1 plus 1 dimension, so 1 spatial and 1 time dimension. So the position of the particle will be given by some real number x, and it's a function of t. Okay. So we call this, this basically is the coordinate in what in classical mechanics is known as the configuration space. Okay. And this function, x of t, say subject to, say, the boundary conditions. Suppose we give some boundary condition that at t equals t naught, x of t, the value of x of t is x naught. And at t equals to t final, the value of x of t final is xf, okay? So x of t subject to the boundary condition, can be any old function, and it's called the path or the trajectory. So these are definitions. We are not talking physics here, okay? So, and then we are going to say, we are going to define a function called the Lagrangian function. So the Lagrangian function is L, and it's a function of x, which is, of course, a function of t. It's also a function of x dot of t. This is something we restrict to this form of Lagrangian because we are doing physics. And for it, generically, what happens is that this Lagrangian function has a very particular form. It has a kinetic term, which is half mx dot squared, and minus a potential energy term. And usually we take the potential energy term to be independent of x dot. Okay, so it's a weird combination. It's not the total energy. It's the difference between the kinetic energy and the potential energy. Okay, so this is called the Lagrangian function. So, and then we have something called the action. And the action is the time integral of the Lagrangian, and the action is denoted by S. And what we do, the way that action is defined is that we take the Lagrangian as our integrand and integrate over dt from the initial time to the final time. Okay? So this is the action. Now see that x of t is a function, right? Because what does x does? It takes you from the interval t, which is in some interval, and maps you to the real number, which is x, right? Similarly, the Lagrangian is a function of two functions, and therefore it is also a function. Okay? We know that if I have a function and I compose it with another function, what I get out is also a function, right? However, the action is not a function, because what are we putting in the action? The action is we fix the boundaries, the initial and the final time, but what we're putting in here is the path x. Okay. So the value of this integral will change depending on what path, what function x we choose, right? Is that clear?
Could you repeat that a little bit?
So suppose you've function x, right? Then the Lagrangian will have some particular function for functional form.
Mm-hmm.
And this integral will give you a particular number.
Oh, so that's why it's not a function.
Yeah, but if you choose a different function, all right. So what I was saying is that the action S is a map from the space of functions of T, because these are the paths, right? Elements of these of this space is paths to the real numbers.
Sir, am I the only one who can't see the screen, or is there anyone else?
Other people, can you see the screen?
Yes, I can.
Let me join in again then.
Yes, sir.
Yeah, rejoin then. Yeah. Okay, so this is the action. So the action is not a function, a map from the space of functions to the real numbers or the complex numbers for that matter. These things are called functionals. So the action is a functional, okay? So precisely what happens with the action, it maps from a particular function to a real number, and the real number is given by T0 to Tf Lxx dot dt. Now, let's note what the dimension of the action is, okay? So the dimension of the action, so you see that the action, the integrand is, should have the dimension of energy, right? And we are integrating it over time. So the dimension of action should be T times energy, times energy, right? But what is energy? Energy is, say, force times distance. And but what is force using Newton's law, this should be the same as mass times distance by time squared. This is F equals to ma, but there's a distance here, so we square this. And then we can now simplify. This goes away. And then the rest we can just write as distance times mass times distance by time. So see that this is nothing but the dimension of r cross p, right? R is distance, p is momentum, mass times velocity. So in other words, the action S has dimension of angular momentum. What else in quantum mechanics, or which important quantity in quantum mechanics has the dimension of angular momentum? Can someone tell me? What constant? Which constant has the dimension?
It's the, yeah.
H bar. So H bar also has dimensions of angular momentum. So, let's file this information away. We shall use it later, okay?